Okay, so in the last module we saw that how we can represent the state of an isolated quantum system. Okay, we saw that it was represented as a vector of a Hilbert space, a unit vector of a Hilbert space. Okay, in this module we'll talk about composite systems. Okay, so before diving into composite systems, we need to talk about composite vector spaces. Okay, composite vector spaces. What are composite vector spaces? Okay, so suppose I have a two-dimensional vector space here. I have a two-dimensional vector space here and another two-dimensional vector space here. Okay, so I have vectors. I have vectors in this two-dimensional vector space of the form. Suppose I can write this as AB, many vectors of the form AB here, and I have vectors of the form CD here. Both are two-dimensional vector spaces. Okay, all right. Suppose I have a basis. Yeah, suppose I have a basis in this vector space. As we saw before, I have basis, suppose 0 and 1. Okay, and I have a basis of 0 and 1 in this vector space. Okay, all right. These are two separate vector spaces. Okay, so suppose I have a vector in the first space. I will say that the name of this space is A and the name of this space is B. Okay, so I have a vector of the first vector space A. Okay, A of the form U equals, well, let's say, suppose like this, A0 plus B1. All right. Okay, and I have a vector in the vector space V. Okay, so these are two vectors of two different spaces. Mind you, they are not the vectors of the same vector space. Okay, so to be more clear, I think I should label the basis more carefully. I will label these as A, basis of the vector space A, and I will label this as basis of the vector space B. All right, so I have a vector, I should write this here, A. Okay, I have vector in the space B, which is V. I have a vector like this, 0, B plus B. Okay, so if I consider the combined space AB, okay, I have a vector in the space A and I have a vector in the space B. So in the combined space or in the composite space AB, okay, in the composite space AB, what will be the vector in the composite space AB? Okay, so I have a vector in the space A and a vector in the space B. So what will be the composite vector in the space AB? Well, we can think of forming a type of product among them. Okay, we can form a type of product. Let's write this carefully. A type of product, a special type of product. How will we write that product? Well, what is the simplest type of product that comes to mind? Well, suppose I can write it as, I know that UA is A0 plus B1 and VB is C0 plus D1. Okay, alright, so if we multiply this out, we can form a product between them. So what will be the product? We can see that A, C, 0A, 0B plus AD, 0A, 1B plus BC, 1A, 0B plus BD, 1A and 1B. Alright, so if in the composite space we can think of the vector UV together in a type of product, and in the composite space this product, we can expand this product and get this result. Alright, so we told that to express any vector in the space A, we need two numbers. The space A is a two-dimensional space. We need the vectors. We can express any vector in the space A using the vector 0A and 1A. Similarly, B is also a vector in the space. A vector in the space B is also a two-dimensional vector. We can express any vector of the space B using the states 0B and 1B. So this UV, this product vector UV, this is a state in the combined vector space AB. Alright, this vector is a vector in the combined space AB. Alright, so to express this vector we actually need four numbers. Alright, we need these four numbers. We need this number and this number and this number and this number. Alright, so in this combined space, what are our basis states? These are our basis states. Alright, 0A, 0B, 0A, 1B, 1A, 1B, 1A, 0B and 1A, 1B. Alright, so this product space, we can think of this as a type of a product space, okay, or a composite space. This composite space is actually four-dimensional. Why four-dimensional? Because we need four basis states to express any vector in this composite space. Alright, we need this, and this. We need four vectors, four basis vectors. So this composite space is a four-dimensional space. Alright, so if we have a system, suppose if we have one system that is m-dimensional, or one system, I mean one vector space. If we have one vector space that is m-dimensional and another vector space that is n-dimensional, then the composite space of these two vector spaces is four-dimensional. Alright, this is four-dimensional.